Okay, good afternoon. Thank you very much, Konstantine, for also the invitation. My presentation is around ARIADNE, which is Horizon 2020 project. And the material has been, let's say, synthesized by Angeliki Alexiou, professor at the University of Piraeus and also the technical manager of ARIADNE, and myself as a member of the ARIADNE team and also work package leader. So ARIADNE is is built around a novel system concept, and a novel system concept, and also around RISs, also whatever that brings beyond sound communications, and overall empowered by AI and or ML techniques. And I say overall, which because in ARIADNE we are trying to put AI in various aspects of all the technical topics that we are dealing. The main use cases that we are treating is around very well known scenarios for front haul and back haul communications, indoor scenarios with users having some mobility, and also networks, ad hoc networks, where here the access point is a moving one. This is practically connected to the previous one. We have RISs. We are also doing some work on design and implementation of RISs at the D band. All the project is built around D band, that is sub terahertz, just over 100 gigahertz. And also this one is trying to depict that through machine learning techniques or a mix of techniques regarding artificial intelligence, we are trying to have an intelligent network management. So ARIADNE has three main pillars. The first one is at the D band to have reliable wireless connectivity, and major importance on that is the work on baseband DSP and the D band front end. I don't see Dimitris Christaridis here. He's from ICOM. They are dealing with the baseband component. The next one is the communications beyond Shannon, and of course a number of physical layer techniques like beamforming design, of course channel estimation, channel modeling, etc. And then the artificial intelligence incorporated in the project, which I have to say that in the beginning more the network management was in our mind to be empowered by the AI techniques, but as the project progresses, then we end up with more and more physical layer techniques to be assisted by machine learning techniques, and I will give one example of this. ARIADNE has three demonstrators. One will be the outdoor one, trying to showcase this reliable connectivity. The second one is an indoor one, hardware demo, but in an indoor scenario based on the meta surfaces designed and implemented within ARIADNE, try to show some functionality of the meta surfaces. And then finally, there is a software demonstrator trying to show the intelligence that has been incorporated to various aspects of mainly network management or system level optimization, let's call it. So I think that also the previous presentation, especially George's one, has already shown what I'm trying to say here, that initially we have a wireless environment which is unknown, so it is statistical, so it brings all the type of limitations that we know regarding performance. And then with the RISs, we try to have a wireless environment which is controllable. And then if it can be controlled through the configuration of and the functionalities of the RISs, then we can have a joint optimization, so jointly optimize the transmitter, the receiver, and the environment, and that is the fact that allow us to go beyond some communications. Also, I think that George covered more than excellent the case of the various designs and the various functionalities that an RIS can achieve. So let's say that theoretically any filter that we desire can be synthesized, at least theoretically. So reflecting the energy to a certain direction, focusing energy to a certain direction, achieving refraction so that we can have efficient outdoor to indoor communications, especially at higher frequencies where path loss is severe, etc., etc. So now with RIS-based wireless networks, what we really have is that we have again the transceiver and the transmitter and the antenna gain, but the channel is a combination of the channel from the access point of the transmitter to the RIS, again from the RIS to the receiver, plus the response of the RIS, which can be controllable, or we would like to control it through a microcontroller. So we have a complex channel coefficient, and now we have, first of all, we have two dimensions and a third one, which is the response of the RIS that we should take into account, describe, optimize, etc. So as I mentioned, ARIADNE is about D-band, so it has to do with frequencies from 110 up to 170 gigahertz, and one of our partners in ARIADNE, Aalto University, has performed a number of measurement campaigns. Three of them, not three campaigns, there are more, but in three indoor environments: shopping mall, the airport, and the entrance hall of Aalto University. And recently we have available also some outdoor measurements, and at the measurements are at 140 gigahertz, and we have been working in various groups within the project to investigate, to analyze the measurement data and come up with fading distributions that closely approximate the measurements themselves. So here we have we see some attempts using the alpha mi, the Nagagami, and the rice distributions. It seems that alpha mi is the best one in all cases, but in some of the cases like this one, also Nagagami and rice give a quite accurate approximation. Although in that case we see something rather peculiar to happen with the distribution of the signal. This investigation has been done by the group of Angeliki Alexiou and University of Piraeus, and this one by our team in Demokritos, where we have investigated. We're trying to investigate line of sight and non-line of sight separately, and indeed, for the first two scenarios, that is the shopping mall and the airport, we see that Viable is very accurate for a line of sight links, that practically you cannot distinguish the curve of the distribution itself with respect to the data, while in non-line of sight links, Nagakami M provides better approximation, and I would say that it is rather something that we could expect. I mean, when we have Viable and when we have Nagagami. Of course, a large number of other distributions, well known as Rice, as Rayleigh, etc., have been investigated. What is quite interesting is that if we see the standard deviation of the small scale fading, then the values are quite low. This is something, here are the line of sight links, and here are the non-line of sight, and although there is more significant variation of the deviation in the non-line of sight links as expected, however, the value of sigma is rather similar in most of the cases for line of sight and non-line of sight links. So I guess that this has to do with poor scattering, which is proved in also from the measurements very easily. So either if you have the line of sight, either if you have the non-line, if you have the line of sight, it is obvious that you have a very powerful component that you receive, and then at the non-line of sight case, again, some very few multipath components are distinguished from the rest of the signal level. So poor scattering might be the reason. I guess it is a reason for the low standard deviation, which I assume that we should start taking into account, because a large number of publications, works, etc., at D-band take into account very well-known models like Rayleigh with deviations at the level that we meet for, let's say, below 6 gigahertz. So we might adapt better to the cases and of the D-band propagation, and still there are not many measurement sets available around the world. There are only few labs that have the ability to do measurements in that frequencies, so still there is a lot of work to be done. In parallel, we have been working on the path loss at the D-band, again taking into account the previous set of measurements at 140 gigahertz. We are using a very simple free space path loss model with 1 meter closing. So the path loss is given as with a dependence on frequency. This term is the free space path loss, which depends on frequency, and its free space path loss at D0, which is taken equal to 1 meter. Then this term, which shows how path loss increases with distance, and that n is the path loss exponent, quite known over all these years and very important though. And this term at the end is a statistical one, which is the shadow fading, is the uncertainty that we still have in various positions, and has a standard deviation sigma. So just to have to have an idea, if we go for the free space path loss at 10 meters at 6 gigahertz, this is equal to 68 dB loss. If we go to 28, then we go up to 80, let's say more or less dB path loss. And if we go to 140, then we go 15 dBs over the previous value, so it is around 95 dB. So this is in a very simple, in a very simplistic way. This is why at these higher frequencies we do have severe signal attenuation, and this is the reason why non-line of sight communications might be not possible in these frequencies. So, excuse me. So, for the line of sight links, we can approach through this model with n equals to 2, that is free space. Practically, this is free space with a very, very low shadow fading. So, practically, it is laser, let's say. It's free space without any scattering, practically. And then we go to non-line of sight links, and we go up to 2.9, more or less 3, and with a standard deviation of 9 dB. So this is one part of investigating the links in ARIADNE, also the small scale plus the long-term fading, and revealing also how important it is to have line-of-sight links, if possible, everywhere, because non-line of sight links are getting very problematic in these frequencies. So the project has heavily incorporated RISs. So a number of studies have been done. I'm only giving 1 or 2 examples of various very important topics for ARIADNE. So here we have beamforming efficiency from a certain perspective, of course. And what is given here is that, okay, if we are quite close, the RIS is quite close to the transmitter, then a large part or the whole RIS is illuminated. And in that case, we see that as the gain of the axis point increases, then the received power increases. So this is what we really want. But then if we go further, and due to the directivity of this transmitted signal from the axis point, then as the gain increases, then even smaller and smaller part of the RIS is illuminated. So we practically start to lose in terms of gain. So we start to lose in terms of received power. So what it means is that we have, this is heavily connected with RIS placement, as one of the last slides by George again. So optimal placement in RIS is also quite important, because this is not going to solve all our problems. We have to adjust between directivity of the and gain of the transmitted signal plus what we would like to do with the RIS. And this work is within this publication by the group of Agela, again in Piraeus, University of Piraeus. And another work which has been done from our group in Demokritos is also connected to the previous one. It's about optimal placement of RISs. This is the system model. Just try to explain a little bit the basics. Okay, we have here the RIS. So when the whole RIS is illuminated by the transmitted signal, then we go to that situation where the best position to place the RIS is either very close to the transmitter or to the receiver. So the RIS should be closer to the transmitter or to the receiver in that setup. So to have the best gain. However, we could still, take this building and move it further. So we go to that situation because YS is this horizontal distance. So if we have this RIS further, then we go to that situation where the best, probably the best placement is somewhere in the middle of the distance between the receiver and the transmitter. So practically what you do there, it's the best point to maximize again the surface of the RIS that you are illuminating. But when we go closer to the transmitter and then the main lobe of the transmitted signal illuminates only a part of the RIS, then you better place the RIS closer to the receiver. Why closer to the receiver? Practically, it's geometrically, it's a geometrical problem because you gain more distance from the transmitter. So again, you illuminate a larger surface on the RIS. So optimal placement of RIS is a very nice topic, and we could imagine more optimization methods that could come in, as of course AI and machine learning techniques, at least at the network level. So, sorry? Yes. 10, max 15. Okay. Huh? Okay. I will try to speed up, but it's 20 something, 24 slides. So, again, AI and ML are entering practically all the layers as we knew them in the past, at least all the layers of the system. So starting from physical layer, going to MAC and resource allocation, network and transport layer. And this is very important. I'm not going to try to explain or even describe this this figure. I cannot. I don't have the knowledge to do that. You can go to that paper. It's a very nice paper from University of Piraeus, CNRS, and RapidMiner, which is our AI expertise in Ariadne. So it is a very nice paper trying to categorize various problems from the physical layer to upper layers, categorize different problems and try to connect how we are going to solve these problems. I mean, what type of algorithms do we need with machine learning? For example, if you want to have real-time adaptation, which are the types of machine learning that you should look into and select the best algorithm that will do your job? So, as I said, in Ariadne, we are dealing with a number of problems from physical layer to upper layers, mainly to MAC and resource management, not going to upper layers. So one of the examples for physical layer assisted by machine learning is channel estimation. So we have this model. The only thing that I would like a little bit to highlight is that we have the RIS, but it, at some level starts to produce interference, because we are going to receive signals that are not only the wanted one, but also from other reflections. Because the RIS itself might get, besides the wanted signal, which is here line of sight through the RIS, excuse me. the RIS might receive also signals from other reflections. So it will start to produce some interference. So this is the standard description of the received signal when we have a combining matrix. The cascaded channel, what also George mentioned, this is the combined channel from the transmitter to the RIS and then back to the receiver. And also we have this omega matrix, which is the RIS phase control matrix, and through standard signal processing techniques we end up with what? We're having the signal equals to a matrix which we can measure, at least having estimations, and then the channel itself, and then noise. So instead of using conventional methods for channel estimation, for example, least square, as in this specific work, we could try to do it through data-driven deep unfolding. And this is what is about in this work, which has been done by Oulu University, the group in Ariadne of Oulu University. So practically these transformations of A and this multiplication with received signal are the input to this machine, okay? And the first input of the channel might be a random one, or full of zeros, and then with the red one, these are the parameters that the machine is started to learn and trying to adjust, and then we have multiple layers, a number of layers, so that at the end of this loop we have the estimation of the channel. This was one of the initial attempts of this group, so this is why they had MISO, first of all, a number of performance figures, trying to connect with the training overhead. It is true that as the number of paths increases, then the problem becomes more and more complicated, and the performance of the technique is not that well. So there are a number of issues that should be solved if we want to to exploit machine learning on physical layer. Of course, this is no need to say that it's offline optimization. Okay, so there is a lot of work to be done also for the effectiveness of the methods, but also how we're going to do it. If we really need online, maybe prepare with offline optimization a number of cases that could be then adapted to our real world cases. And the last example is for user association, exploiting again machine learning. So, okay, this is a standard scenario. Let's say user association is quite important because we have the D band, it's directional links. Then even the users themselves can become blockages for other users. So what we try to do is to formulate a user association problem and then try to solve it with machine learning. And it was not that easy because I have to say that these are two different worlds, one of the communication and one of the AI world. So here in that case, University of Piraeus and ourselves, Demokritos, worked on the preparation of the simulations at the communication side, let's say, and then RapidMiner did the rest of the work on the optimization, on solving the problem with their techniques and tools. So although it is a very simple scenario at the communication level, we have what we did was practically we were simulating an area, and then we're dropping users and trying to see which of these users with respect to various access points, had a line of sight. Which of them was blocked, totally blocked, and partially blocked? And then this is, let's say, the problem. Okay, with some other restrictions. And then we needed machine learning to do what? Somehow to solve the problem and associate each user with only one access point. In that way, that minimizes the number of users that are blocked. But also having some standards on the received signal, of course, thus at the performance, and then try not to overload certain access points. So this is, let's say, the framework. So I want to mention that their solution was based on meta-heuristic optimization, and then after providing the first solutions, they were training machine learning models. This is the technique they used. So what the result is that we had from 741 users. Then with that procedure, the vast majority of the users were allocated to access points having line of sight. 100 of them were connected to a certain access point with only partial block of the blocking of the link. And then out of 125 access points, only 99 of those were used. So we have kind of efficiency because we are not using the whole system, and only 22 of them were overloaded. So we defined the problem from the communication point of view, and then we were cooperating with AI experts to find the solution. This is a visualization of the problem where the red dots are access points that are overloaded. The gray one you cannot easily distinguish, but where is it? No, this is red also. Let me find one. Okay. That one, for example, because gray is not that obvious in the, for example, here. The gray one are not overloaded. The red ones are overloaded access points, and then around the dots around are users that have been associated to the certain access point, and then the lines, the attributes of the lines give more insight to various information, and this is based on the tools of our expert RapidMiner. So I think that I have done my best to give you an overview of what ARIADNE is trying to do. We believe that we pave the way for the AI native wireless systems, information theory assisted by electromagnetics, which is, I think it's one big thing for the future, of course, Internet of Materials. And for those that are interested, there is a special issue at IEEE JSAC on Beyond Sound Communication, guest edited by ARIADNE. The submission deadline will be 1st of August, and this is a map with the partners of ARIADNE. Thank you very much.
And thanks for keeping the time. Okay, questions for Dr. Lazarakis? Questions on the chat? No. Okay. So maybe on an anecdotal note to say, I was looking at the agenda, I realized I have been on EU project with every single presenter today. Yeah. Okay. But with you, we've been in the first ever EU project I was, and together with Professor Alexiou, who could not be here, which was fitness, right? Yes. Right. In the FP5, 2001, right? And I think it was probably the first MIMO project, the European project ever, right? Yeah. So anyway, thanks again. Great to see that you're still active in those fields.